All right, party people, let's get started. So if you watch the lab, you probably have a pretty good sense of what's going on. So we'll do this fairly quickly, but let me zoom in just a wee bit. So a PV bus, I didn't call it a gen bus, called it a PV bus, but sometimes it's easier to think of it as a generator bus, and depending on the software application you use, it might say gen bus, it might say, because you can select when you do a load flow as to the bus type, but PV bus, you only schedule P. That's the only real power you schedule. The Q, and I talked about this in lab the other day, the reactive power cannot be scheduled, and the reason why it can't be scheduled is because it needs to output or absorb as much power within limits to maintain that voltage at whatever is specified, okay? So that's why you can't schedule it in advance, because you don't know how much reactive power the system is going to supply or absorb to get that voltage that you need it. So as a result, the only power balance equation that we can write is delta P at that bus, right? Again, the f of x equations we are solving or checking to make sure we have the right values are the power balance equations, right? And we write power balance equations because we're trying to solve for the unknown voltages and angles, right? Well, we already said we know V, right? So we know what the magnitude of V is. We can control it. We can specify the magnitude of V. So as a result, we don't have to solve for this because we know what it is. We've specified it. So of the unknowns that we have to solve for are the bus voltages that we have to solve for, magnitude and angle, at a generator bus or PV bus. We already know what V is. We only need to solve for theta, okay? Which is a good thing because we can only write a single power balance equation, okay? So you're going to write your power balance equation for theta. And if you remember when we partitioned our Jacobian matrix, here's our delta P's and then our delta Q's and our thetas and our V's. When we partition our matrix, our theta is primarily going to be determined by real power flow, right? We talked about that from the transmission line operation. So sensitivity analysis, it's far more sensitive. Real power flows tend to be far more sensitive to theta changes than to voltage changes. All right? If you want to solve for Q, how would you solve for Q? Yeah, you just write a Q injection equation, right? All you have to do is write Q injected, and then you can solve for the Q, okay? So here's an example of a 3-bus with a PV. So we essentially have a slack bus here, or a voltage bus, a load bus here, right, which is PQ, and a generator bus, which is PV. If you note, that is the magnitude of the voltage, and the power is specified there. You'll notice it says 63 megavars. That's because this is actually spitting out the results of that value, okay? I mean of the calculations for P injection. So we can write, if we do it our table, right? Remember our table? What was our table again? Bus, knowns, unknowns. Let me move this over just a little bit, give myself some room. Equations, anything else? Okay. So we got bus 1, bus 2, bus 3. Bus 1 is a slack bus, so we know V and theta. We do not know P and Q. What equations can we write at the slack bus? No equations, because we can't solve for power balance. But that's okay because we have no variables to solve for. Bus 2 is a PQ bus. So we know P and Q. We do not know V and theta. What equations can we write? Let me actually say, what equations do we write? Delta P2 and delta Q2. We can write power balance equations because we know what the scheduled power is. What variables do we need to solve for? These are the ones that we need to be able to fully characterize the operation of the system. V or theta, delta or theta, either one, yep. So our bus 3 is a generator bus. What do we know at the generator bus? We need P3 and V3. What don't we know? And what equations can we write? Delta P3 is the power balance equation we can write. And what variables are we going to solve for? Theta 3. If you want to append on this table, and I don't know if you want to or not, but when finished, load flow, you can calculate all those unknowns, right? So you can calculate P and Q, right? But this is only after the load flow is complete. You can calculate P and Q. What would I calculate here? You can, well, you know what V and theta is because you saw for that as part of the load flow. But over here, you can actually check to see if you want to check. But you can check and see if P2 and Q2 match your values. But you should know that that's the case anyway, right? Why? Because you've already solved your f of x that said power balance at that locations are 0. So you technically don't need to calculate anything there because you already know what the power injected at the bus. It's whatever the scheduled power is. So there's no work that needs to be done. And over here, you would just calculate Q3. Okay? Does that sort of add additional clarification or confusion? Or I do not know Q3. It's an unknown, right? The Q3 is going to be whatever it needs to be to maintain that bus voltage. Here's that example written in MATLAB. Again, nothing up my sleeve approach to doing this. So you can take a look at all those equations. We're not going to derive them again because that can be tedious and time consuming. But you can take a look. But here are our f of x equations. Here is our Jacobian equation. So remember our Jacobian is delta P2, delta P3, delta P3 and delta Q2, right? Because bus 2 is the load bus. So then I have theta 2, theta 3, and V2. So notice, right, I always put my P's and thetas and V's together, even if it goes out of sequence, right? You would think delta P2 and then you'd have delta Q2 after because it's 2. No, you order all the P's together, all the Q's together, all the thetas together, and all the V's together, and you do that. So if you look over here, J11 is the partial of delta P2 with respect to theta 2. All right? So you can take a look at that and verify. Do I need to zoom in, or is this legible enough? I can't remember. I think I have to zoom in for MATLAB. Better? Okay. So this is exactly the algorithm that we've done for a 2-bus load flow, right? 2 equations. It's the same exact set of equations. And so if you look here, my delta x doesn't change, right? It's negative j, and I put left divide, but it could be raised to the -1 or inverse, times your f of x equations, and then I just update my variables. So I did a slightly different approach here to see how to combine those variables into one. You can take a look at that. And then I called it T2 instead of writing it out theta 2 or delta 2, so just trying to simplify some of the work, and you can figure it out from there. And then at the end, I go ahead and I calculate, what those angles are, the final angles are going to be in terms of radians per second, degrees. I also check my error, right? So that's that vector 2 norm. So I check my error to see if it's greater than 1% or 0.1%. And I also stop it if it's greater than 10 iterations because they should converge in less than 10 iterations. What we were doing for lab the other day was we ran through, and I think to get less than 0.1%, you needed 3 iterations to go. So I've never seen one that takes 10 iterations. So here's processing. You can take a look and see what your results of your initial guesses, and you can see with my initial guesses, just all 1 at an angle of 0. Then here's my Jacobian, and sorry for the page. That's the problem with MATLAB. It doesn't know to try to keep the matrix together, so that's why it's kind of split on 2 pages. Then I update T2, T3, and V2. Notice my delta P2 went from 2, now it's down to 0.1, so a pretty big change, right? Delta P2 should be 0, so 0.1 is a lot closer to 0 than 2 is. Here's my Jacobian, updated now with a bunch of different numbers. And that's not as important to me. And you can't always tell if those Jacobian numbers should be close to 0. That's not necessarily something that's going to give you any information. It's only those f of x evaluations. I update T2 and T3 and V2. Now I go ahead and check to see what my dPs are, or my delta power balance equations are. Now I'm really close, but I'm still greater than 0.001, right? You can see both dP2 and dQ2 are greater than that. So I'm going to run through another process. Jacobian, theta. And now I don't even plot out the dP2, dQ2, because I was pretty close here in this case. So I only had to do one more iteration, and I got that. So my final angles are negative 7.5 and negative 2.7. Which should match pretty closely to the results in the value, in the slides. This is your final voltage. Obviously, I didn't display that in anything different because there's nothing to multiply. That's the per unit voltage there. Okay? Do you remember what the voltages are? Bus 1, 2, and 3. 1 was 1 at an angle of 0. What was bus 2? This is for the lab, right? This is not the lab problem. This is the different problem.
The lab was 1.05, wasn't it?
Yeah, but I'm talking about in the notes. Let me pause it. I'll go back and I'll pause it. Otherwise, it'll give us a hiccup. So let me pause it. Okay, so this is 1. And this was a certain power. This was 30. And I think this was 200. Is that correct? What was the P and Q at bus 2?
200.
And 100?
Yep.
So this voltage here is 1. This voltage here is going to be 0.94 at an angle of negative 7.469. Whoops. And what was this voltage here?
Where?
At bus 3. 1 at an angle of, do you remember what that is? 22? Negative 22? I can pull it out. Negative 2.7. So, you got to sanity check it, right? Because we're engineers, or almost engineers. We got to make sure if our results make sense. So, does real power flow from a higher magnitude, reactive power flow from a higher magnitude to a lower magnitude? Well, this one here, I didn't calculate my delta Q2, so you can't tell here, but clearly I can see that I've got 100 megavars flowing here. So you got some reactive power going in there. I think this is actually 63, is that correct? It's 63 in. Question?
Yeah. Where'd you get the one at the angle of negative 27?
Negative 2.7.
Where'd you get that from?
I just multiplied the radians by,
All right.
so I calculated that in a script file. So I have 63 in, 100, so you can see here that with these magnitudes the same, this one's providing 36, this one's 36, and this one's 63. So you can't tell exactly if it's going to be shared because it's not exactly that case, but you can see that there's some sharing there. But more importantly, look at the magnitude here. 0.94 is much lower, so I'm getting 100 megavars. All the reactive power is going there. Same thing with the angles. This is 0. I think this is actually in, not out. This is putting in 30. This one right here has to put in 170. So you can see its angle here is going to be slightly less than that angle because it's putting out 6 times more real power. But look at the angle here, minus 7.4. So all the real P flows in that direction. Comment, question?
For the angle, so the power is flowing from the larger angle to the smaller angle?
Real power flows from the higher angle to the lower angle. Yep. Reactive power is the magnitude.
So if one of those buses was a positive 20-degree angle,
Yep.
it'd be more power than 170, right?
So the question is, if this here, let's just say the slack bus is 1 at an angle of 20, you'd have way more power coming from your slack bus. So in this case, remember how we talked about solutions that aren't real or not converging? That might be a case where you have non-convergence because you just can't get 30 megawatts of real power out of the system. So your slack bus, you don't want it to be set too sky high because you have some problems actually doing that. And that's the only bus, right, that we can set the angle on, correct? The only bus that we can set the angle on is the slack bus. The generator bus, we have to solve for it. The load bus, we have to solve for it. Okay? Any questions? So again, nothing up my sleeves. You can take a look and see if you get similar results. If you want to go ahead and try your power balance and see if you get the Qs and all that stuff, you're welcome to. I didn't include that in there, but you would just write your Q injections for those buses, and you can check to see if you get the results that are shown on the slides. Any questions on how to add a PV bus? Because that's it. As we talked about in lab, there's only 3 cases of bus, right? So you have a bus where you have 0 equations, or 0 unknowns, I should say, that you have to solve for. 1 or 2, right? Would you ever have 3? No, because the only thing you're solving for is V and theta. If you know V and theta at each bus, then you can solve for the power flow in the system. So the max you'll ever have is 2. That's why you only have 3 buses, because you only have 3 possible combinations of knowing or having to solve for those variables. Okay? Questions? No questions? Good. Here's your chance to prove your worth. It's a 3-bus system, and I tweaked it a little bit. What's the tweak? Thetas? What does that mean?
You added. Looks like you added some. They're not 0.
In the past, right, our Y bus was just simply equal to J times a bunch of B's, right? This one has a G plus JB in it, doesn't it? So remember when you've written your equations in the past, you've always said G was equal to 0. That is not the case this time. So you can't throw those away. So make sure when you do this problem, your Y bus, this is not in the format of G plus JB, is it? These are in the format of complex impedances that are in polar form. So the first thing you need to do is do a polar to rectangular conversion, right? Once you have that, everything else should be the same. You're going to implement the delta P's, delta Q's, based on running through those tables to figuring out what variables you want to know or need to know. Go from there. This is your homework. When would you like it due? Tuesday? Well, I'll post the video now. Well, because that brings up a question. So the question is, when do we have our next test? Do you want to finish the slides in this class or this material and then talk about the test, or do you want to do that now? Let's. Yes. All right, just the slides then. So this is just sort of summary about how to apply Newton-Raphson. So what are the advantages? It's a very fast conversion, right? 3 iterations. You've got to be reasonably close to your solution. Reasonably close. This large region of convergence is essentially telling you that it is going to work through pretty hard to make sure that you end up with a final solution. So they oftentimes converge. As a matter of fact, if you look at, I think we looked at Power Tools for Windows a few folks the other day, the only actual method that they had available for load flow was the Newton's method. It used to be that there are 2 or 3 other methods that you would see. Now this particular software application only had Newton's method. Gauss-Seidel is another method. We'll talk about it, but we won't really get into it because nobody uses it unless Newton-Raphson doesn't converge. So, but it's another way to solve nonlinear. Each iteration takes a long time. Why? All because of this. Inverting an 80,000 by 80,000 matrix is a lot of work for a computer. Okay, computers are getting faster. You're networking them together. You can do more with them, but inverting a big matrix like that, even if it's sparse, so sparse matrix means you have a number here and then you have, so many zeros elsewhere that it's almost all zeros. And there was a lot of work done to do what's called sparse matrix algorithms to sort of speed up the work. I don't know if that's still being done. When I was in grad school, there was all kinds of work about sparse matrix techniques and all that stuff. All the stuff that I've seen today that I've looked at doesn't really describe sparse matrix technique because processing power has improved dramatically. Back when I was a grad student almost 30 years ago, it was a completely different world. You didn't have, a 386 or 286 was all it was at with maybe 8 megs of RAM. So now, your phone has, 50 times the processing power. So sparse matrix techniques, yeah, it's cool, but the processing power is not a problem like it used to be. So I don't know if they still do it, but that is an issue. Super, super common in the algorithm. And then you can use Gauss-Seidel, which is essentially doing a current injection approach. We won't get into it here. There is some discussion about Gauss-Seidel in your text, so you can take a look into that. But again, we won't cover that here. Oop. So why do we do so? Why do we spend so much time on load flow? Because the system, again, has to be stable for n-1 contingencies. And one of the stability things is no lines are overloaded and voltages that are out of whack. So what ISO New England does constantly is they're always running these contingencies in the background saying take this strongest source out of service and then see what happens. And then perhaps take the second strongest one out of service and see what happens. Because you have to be able to handle that loss of the biggest case contingency, and you have 30 minutes to get the system back to a happy point. So that's like you can operate for 30 minutes under emergency conditions, which is the grid is, not in a great place, but it's maintained stability. But you only have 30 minutes to get back to the place where you can take another hit on your system. You can lose another next worst case scenario. And so what contingency analysis does is not only looking at that first one, but also looking at that second one and beyond. And so where do you put a wind farm, right? How a wind farm gets integrated into the system and how its power moves can dramatically affect the reliability of a system. So upgrades to the system. Do I need to add another line? Do I need to add another breaker position? Do I need to increase or decrease the impedance here? And so if you go into ISO New England's website, there's something called a Q, which You basically say, I want to build a power plant at location XYZ. You fill out an application, you pay some money, and then you get a number. You're in the queue. And all the projects in the queue in front of you get analyzed first, and then yours gets tacked on after that. And so whenever the analysis is happening for future projects that are after you, they have to include that. So any changes that need to be made to the system as a result of their projects, you don't have to pay for. But any of the system changes your project imposes, you have to pay for those. And that could be very, very expensive, hugely expensive. It's expensive. So the New England Clean Energy Connect, why are they adding a bunch of 345 lines and adding breaker positions and rebuilding certain sections? It's because they did this contingency analysis to figure out, okay, if we lose this line, what's going to happen? And so that's what ISO New England has done. And one of the students, former students here, he's in the 10-year look ahead, which he looks at proposed projects or the system, how he thinks it's going to look in 10 years to figure out what are the problems going to be in the system. So there's a 10-year look ahead because you're projecting load growth, projects, are projects going to go away? Are they going to stay? And obviously it's a guess because 10 years is a long time horizon, but you got to start someplace. And so that's a major, very important project. Question?
How about the grid out in California where they've turned off major parts of it now? When they go to turn all that back on, what kind of problems are they going to have with balancing the system?
So the question is, because of the fires that are currently or ongoing or probably will never end in California, which is not to make a joke, it's just because of climate change, you're seeing that PGE is turning off a lot of electrical system, not by means they have to turn off customers, because what happened last year caused dramatic fires was they had an arc that might have touched off massive fires. So to prevent the fire from being started because of PGE, not because of not prevent fires, but prevent fires being started because of the electrical company, they've just turned off all these lines, and so loads are gone. So what happens is when you lose load, you also have to turn down generation. So you have to tell generators to turn off or turn down. And when you're ready to turn on customers, you need to know approximately how much load you're going to pick up. And then you have to tell the generators to be up and running and ready to go, to have a big change in their power demand. So sometimes they'll try to stagger it. So they'll turn on a transmission line, and then they might have turned off a bunch of distribution circuits, and then they'll turn them on one at a time to sort of limit that. But one of the challenges with figuring that out is something that's called cold load pickup. So what happens when power's been out for 5 minutes? It's annoying, but you know what? Not much happens, right? If it's after 30 minutes, what's happened? House is getting cold, your furnace might be cold, your refrigerator has warmed up a little bit, your freezer, you haven't had lights, you've had to delay a lot of activities because you don't have power, right? If you have a well pump, it's ready to kick on as soon as it happens. So cold load pickup in a, what's that?
So that means it's going to be a surge when you do that?
It's going to be a surge, but more importantly about a surge is the line is going to have a full load greater than normal, right? So the load is actually going to be greater because you don't have something called diversity. Diversity, from an electrical perspective, just to be clear, I mean, I'm not talking about diversity from different perspective, but load diversity, maybe I should caveat it with that. Load diversity means I'm not going to be running my washing machine or dryer machine at the same time my neighbor is, or both us neighbors may be running at the same time, but not all the entire neighborhood's going to be running it. So we're not doing all the same activities at the exact same time. So you can include load diversity so that you don't have to assume that everybody's running full out on their electrical boxes. But that's what doesn't happen with cold load. With cold load happens, everything is on, baby. It all starts at once. So you actually have conditions where your system is under stress because the load is so high. And your cold load pickup is higher than the actual tripping characteristic of what it should be. So the line is stressed out, but it's only going to be stressed out for what, maybe half an hour to an hour? So when is cold load done?
What would it be the starting currents of all the
That's inrush, that's different. This is maintained. Inrush, you just deal with it. You're going to have some low voltage, but you can deal with that pretty well. Cold load pickup goes away as once everybody's diversity starts to come back into normal, you actually have diversity. So when your current is sky high and then it drops below your normal full load, then it's no longer a cold load condition, right? Now we're starting to have diversity. So what's happening in California is they have to anticipate that. They're going to run for long periods of time, maybe an hour, where you're going to have massive power demands, overload, and then they'll actually know or not exactly, but they'll have a sense of how much power is being demanded, and they'll just switch one person on, then the next, and the next. When I was in Queens, I sort of lived in Queens for a little while, and there was a plant called Astoria Unit 2 that back in the 70s, was anybody here born in the 70s other than a couple of us? So in 1976, I think there was a blackout in New York City, and the whole city went dark. So I just have to caveat when I say black or dark, that's not meant to be derogatory. That's just a technical term for clarification. So, you know, sometimes you hear a blackout, but that's not meant to be derogatory. It just means that there's no lights. So just for clarification up front, I just want to be clear that that's not meant to be derogatory. But black start capability is very difficult, right? There's no power. So how do you get a big generator online without actually having a lot of power? Well, in New York, when they had the blackout, they actually started the entire city off Unit 2 in Astoria. And how they did it is they barged up a generator from the Navy. So they had a Navy generator. It was on a ship that, I don't know, was maybe 5 megawatts. They barged it up the river. They tied it off next to Astoria Unit 2, and then they brought Astoria Unit 2 online, and because they hadn't really anticipated, you know, what was going to happen in terms of being able to throw people on, they were super freaked out. So normally you run at 60 hertz and whatever the 1 per unit voltage is. I think they said they ran it at 60, the generator at 63 hertz. They turned off the high-speed trip. They turned off the high-speed trip, and they ran the voltage at like 110%, because when they closed the switch, that generator just had all that load. They didn't have the ability to switch things on and off. So the generator had a tremendous amount of load and almost tripped because it had dropped off in speed and voltage so quickly. And that's because of inrush conditions. But once, you know, it brought everything back up, then they were able to launch and bring up other generation before they brought on other load. So Unit 2 in Queens that I've actually been inside, which I don't even know if it still exists. We were trying to repower it back. They were actually trying to tear it down back then, but it was built in the 50s. But it saved New York City. I guess there's no glamour because they were trying to tear it down in 2000. So
it like bogs down for a moment's time?
just like a generator at your house, right? If you have a generator at your house, and what happens when you flip on a load, you hear it go, whirr, and then it picks back up because you got to get more fuel in. Well, it's the same thing. This generator doesn't essentially have any load on it. All of a sudden, you dump 50 megawatts on. It has to get steam in there really quickly to pick up that 50 megawatts of load. So their protection protocols are probably mostly bypassed because that's an emergency condition. So they probably just, in the breaker for the generator breaker, they probably just opened it up and just said, no, breaker's closed and we're not going to trip it unless, you know, we have a super critical condition where they had somebody standing there with a push button. Ready to go. Because everything at that point was, you know, you can't protect the generator. You just have to hope that you can get online. But back in the day, stuff was built so much like a tank. I mean, if you walked around this facility, they had 1,000 MCM ground wire. Never seen anything like it. I mean, usually you see 250, 500, 1,000 MCM everywhere. They had 750 MVA rated 13.8 kV gear. At the time, that was still the highest rated equipment you could buy. So everything was gold plated. It was just the best of the best. And so it was a tank. If you did that today, I don't think any plant can handle it because the stuff today is about efficiency and cost. It's not about, you know, surviving these worst case things. It's just a completely different world. So if that happened today, that's why if you look at NERC just issued an OP24 that all these companies are required to submit. They're doing all these analyses to say, hey, does your system coordinate with the utility system so that if there's a problem like what happened in 2003, they'll coordinate. We won't have 26 states that trip offline because of a fault in Ohio. It'll just trip off Ohio. And so NERC is sitting there pounding you and issuing fines. And NERC has authority to hit you with fines. So you comply or else. Any other questions on that?
With the inrush current for like starting on the furnaces in the winter, they must size all that fusing and everything.
No, because the inrush currents on furnaces, I mean, my furnace I think has a half horsepower motor. So even if it was 7 times lock rotor or half horsepower, that's going to be, that might be 20 amps.
But even with like if half the state lost power, I mean, we just had 200.
But again, it's only going to get that inrush. It's going to happen for a brief moment in time. So the only thing we'd have to worry about would be any instantaneous elements. Most of the other stuff, the short time elements, wouldn't trip on that. So if you want to learn more about tripping and instantaneous and short time, the follow-on class to this one, which is Power 3, which counts as for the concentration in power systems, is there. Also, for those of you interested, Eet422 was just approved yesterday for population and environment, so you can kill a gen ed, and that also counts for, at least for the EET concentration. I'm not sure for ECE, but you can take a look.
Which class was it?
EET460. It's a renewable. It counts for renewable minor, and it also counts as a gen ed now, so you can use that for one of your.
It just got approved yesterday.
Yesterday afternoon, yep.
Oh, I was trying to sign up for that class. It didn't work.
Oh, well, never too late. So for those of you who are looking, trying to maximize our efficiency and yours. So here's contingency analysis, where literally you just enter a bunch of cases. Take this out of line, next. Take this out of line, next. Take this, and on and on and on, and you just walk through, and it's going to look for the worst case. So this one actually automates the process of how to do contingency analysis, which is also what PSSE does. Most of us will not be doing that unless you go work, like I said, for ISO New England, or you do some analysis, you know, for generator projects. Yes, sir.
When these companies do these fault analysis,
This is not a fault analysis. This is contingency analysis.
contingency analysis.
Yep.
So it's all in a simulation. Do they actually at some point go and physically try this out to see if all the equipment actually holds up?
So the question is, would they go out in the real world and mimic what the contingency analysis is? And the answer is absolutely not. If you did that, you make the system more expensive to run, right? And you also basically put the system in stress. So you don't want to check this, you don't want to cause a problem that actually you're not sure if it's going to prevent you from tripping or not based on the simulation. So you simulate it and you check your simulation results, so there are events that you can compare your data to see how close you are. But no way, you don't take anything offline unless you, they will do maintenance on lines, but they try to do those under low load, like on a weekend, on a Sunday morning. So they'll take stuff out of line. I was talking to a guy a week ago, and they went to Astoria. Actually, they were working on a 345 line, and they showed up all smiles, ready to work. And it's like, oh yeah, well, we'll start that tonight at 8 o'clock. They weren't told that all the work was being done at night. They just assumed they could show up and do it during the day. And the company's like, no, are you crazy? We can't put this substation under risk during the day. You're going to do the work at night. So they showed up and ended up working overnights because it's much safer. That's the other downside of working in this world. You get to do all your work stuff during the day, but when you're actually switching things in and testing things for a system that's actually up and running, you're doing that always on nights and weekends. Nobody's going to allow you to test a system that is important, that's even remotely important to the grid, unless you minimize the risk. And how do you do that? Nights and weekends. So that's contingency analysis. We'll do this fairly quickly. So I talked most about it, right? So we have n-1 contingency, and we want our voltages to usually be within plus or minus 5%, no line or transformer. Notice we don't talk about frequency. Frequency limits are much tighter. If the frequency on the grid varies more than like 0.01 hertz, that's a big deal. So voltage changes all the time. Frequency hardly ever changes. You'll see it, but if you were to look at a plot of a frequency, you'll see something doing this. But this might be 60.003, and this might be 59.997. So less than 1% change in the frequency is tolerated. Much, much tighter operation.
Now, does generation drop out? Do they drop out and the frequency starts to drop?
Yes. Well, actually, it's not generation. So the question is, what happens on bad frequency condition? Usually it's under frequency. There are actual automatic systems that the transmission owners have, like Amera, Avangrid, Eversource. All those companies actually have UFLS, under frequency load shedding schemes, that are automatic. They take over within a certain period of time. If the frequency is below value, bye-bye this substation. It's going to be de-energized. It will happen automatically, because the only way you can save frequency, you can't ask generation to pick up, but you can dump load really quickly. So they'll shed load. You would never want to shed generation, because that's going to exacerbate your problem. But if your frequency drops, you'll under frequency load shed all day, every day. They'll just dump you. And I don't know who they decide dumps and how they figure that out. I've never seen that level, but you can take a look. Avangrid probably has some description on their UFLS. There's a lot of work to do that.
Is that on like high load days?
Yeah, typically it would be a high load day, or perhaps if something, like I said, when we talked about that contingency analysis, if a trip occurred and somebody hadn't postulated something correctly, maybe they had a voltage or a frequency that was lower than they expected when they did the study, and so it might have tripped offline. But at that point, you've got some explaining to do. If your UFLS trips because of an expected contingency, NERC is going to, slap you around pretty good.
So I know when I worked at the paper mill in the middle of summer, the utility would call up and they'd have like really great prices if you would agree to shut your manufacturing
Right. So
down.
the comment was, when somebody worked at a mill, they would be contacted by the utility saying, we'll offer really great prices. Well, that's important. We can take a look at that. But if you go to ISO New England's website, you can take a look at the real-time energy price. So in the summer, when it's hot as heck, everybody's tired. It's the third day of a heat wave. You're tired of the heat. You're just finally giving up and you're running your air conditioner, as is everybody else. So now the grid is super stressed. It's at its max value. All those peaking plants, all those inefficient, very expensive to operate plants are called upon to run. So the dollars per megawatt hour, you might be spending $800, $900 a megawatt hour, where if you were to look today, it might be $40 a megawatt hour. So you're going to get a call from the utility saying, any way you're willing to shut down? Because they don't want to buy power at $900, because their costs are fixed, right? They can't sell it to the customer for more than the agreed upon price. So if the power goes up to $800 or $900, the utility is going to have to eat that. So if they can get the big company to shut off some load, it's going to save them from buying power at an exorbitant rate. So that's the reason why they do it. It's not because of the frequency. It's just because all the generation at that point is very expensive. And if they can shed some load, you can reduce the costs. There are special days too. If you look when it's really peak load, ISO will issue an alert. They'll issue a hands-off day. Don't do any maintenance. Don't touch anything. Don't trip anything, because you could trip something. And so they put these warnings out there requesting that no generators or transmission companies do any work, because if something happens where somebody screws something up and they trip off, the contingency stuff is really dire. And then your price per megawatt hour might go to $3,000, $4,000 a megawatt hour, which would really, PGE filed bankruptcy because of this in the 2000s, because they were not allowed to sell it at a high price, but they were buying power at $2,000 a megawatt hour. Anybody know why the costs were so high? Yes, but there was one other thing too, and the company no longer exists. Enron. So they owned a lot of generation there, and they were actually taking bearings that they could work on equipment, and they would actually throw it in the trash to say, well, we can't get our generation on, because that would have reduced the cost. But all the other Enron generators were at $2,000 a megawatt hour. So one 10 megawatt generator, which might have brought the cost down to $1,000, they just said, well, we won't run it. So that bearing, literally, they threw equipment in the trash, say, we can't maintain our equipment. We don't have this bearing. So there was a lot of snarky stuff there. Again, I think we talked mainly about this. We have limits. We have thermal, voltage, and stability limits, and it depends on the line length is the bigger one. You can't directly control AC flow. You indirectly do it, right? So you bump up a voltage, you change a phase angle, right? That's why we have phase shifting transformers. Why do you think we called phase shifting transformers? It changes power, right? phase shift means changing power. So those big fancy phase shifting transformers, their whole purpose in life is to change the phase to move more power. So you can indirectly control. You're not directly controlling real power. You're just controlling the phase angle and the voltages and hoping that you'll be able to do it, which you can do a pretty good job. But again, it's not like you're putting more water into a tank or less water where you can control the level directly. This is all indirect. Oops. I think we went through this in enough detail. So our slack bus is the pickup, and you always have to have some sort of a slack bus in your system. So in the real world, you have to have sufficient generation located in a few areas that are basically running in load following mode. So sometimes main independent station actually operates their generating area as a slack bus, but they have to get paid for it because if they're updating their P and Q real time, they only get paid for the megawatt hours they sell. So if they have to ramp down their real power output, they're not getting paid as much, and so they're willing to produce less power, but they're going to get a payment based on the fact that they can actually operate as a slack bus. So main independent station, and most generators can do that now. They can operate based on maintaining a voltage, magnitude, and angle, essentially. Real size power flows, hundreds of thousands of buses are not uncommon. If you were to do a smaller industrial facility, 50 buses. So if you were going to buy a license for an analysis program, 50 buses, would do fine for most places. If you're starting to get into the transmission and distribution level, 10,000 buses is not that uncommon. And so guess what? The companies that sell this analysis software, how do they mark it up? It's based on the number of allowable buses. So you can buy power tools for Windows for maybe $2-3 grand for 50 buses, but if you want to go to 2,000 buses or unlimited buses, you might have to pay $10,000-$12,000. Is the software any different? It's the same exact software, it's just a limitation. So that's how they get you. It's based on, hey, if somebody's doing an analysis of a system with 2,000 buses, you're not just a mom and pop shop doing something like that. You've got more expensive stuff. So kind of how it rolls. I don't set the prices. That's what's happening. You can also do some non-linear stuff, right? With HVDC, FACS, anything with phase shifting. Aspen does have the ability to model that. We don't get into that because that's, again, more of an advanced topic. I think we talked mainly about this. Here's a simulation where you can look at contingency analysis where we do some indirect control. So here's our 3-bus system. And if I'm trying to be a generator bus maintaining 0 power here, and I've got my load here, and this is 1 per unit, this is 1 per unit, you can see that I've got all the real power going here, and my reactive power 71 and 100. So I've got more I squared Z or X losses. So this line is at 124% of capacity. So it is overloaded. What if I now put some real power out? So now I bump this up to 95 megawatts. This drops down to 105 to make up the difference. But look at my line. Now I'm right at 100%. I can't tweak it too much because I've got 92% going through this line. So I might be able to do a little bit more, but not much. So if I was to look at this system design, this is a poorly designed system, right? Because this system only has one line that is so lightly loaded, 3.5 megawatts. Forget it. This is a really poor design. So I wouldn't even put that line over there. What I would probably do is I would run a parallel line into that location. And parallel lines are not that uncommon. If you were to go to Sandy Pond, which is a DC substation where it terminates in Ayers, Mass., there's 2 lines that go from Sandy Pond to Wachusett. So important that they actually have a parallel line. You don't see them all the time, but they're not unheard of. So they go from the same location. Maybe a different path, but same location. A balancing authority, so we talk about we want to share, right, with our neighbors. So ISO New England is trying to get power from New York ISO. when they need it. So if I can buy power from New York that's cheaper, or I can sell power to New York and make a profit, you can actually schedule the power in these interconnecting tie lines. The line between New York and ISO New England, or Hydro-Quebec and ISO New England, those all have to be for buying power. So the balancing authorities actually make sure that the power flow through those lines is what's agreed upon. If it's not, there's something called automatic generation control what'll bring things down, and then either the company or the utility that's responsible for maintaining their power that's too low, they'll have to kind of come up with generation elsewhere, or it'll get choked offline. How do they choke it offline? They start to decrease the voltages at the bus that's near the tie lines, so they actually can monkey with it. Here's a map of the balancing authority. So as I mentioned, and let me zoom in a little bit. We are way up over here. So we are in ISO New England territory. We interconnect to New York ISO, which is the balancing authority there. We also go to New Brunswick ISO. What this map doesn't show, and it does show a DC line, this actually doesn't go through Maine. It actually stays above. But right up in here is not ISO New England territory. That is Northern Maine ISO, managed out of Bangor. So there is no direct high voltage connection, 115 or greater, that goes from ISO New England into the Presque Isle area. So if you look at a map, that's considered an island. All its connection goes up and through this way. So it has its own independent system operator in Northern Maine. So from an electrical perspective, Northern Maine is not considered part of New England. A couple other things that's interesting here. Remember how I said, why are we going to run another DC link to Canada? Well, look at all the lines going to Hydro-Quebec territory. They're all DC, right? That's because, again, they run asynchronously from their neighbors. They don't have to run at the exact same phase shift. Texas also, if you notice, it's got all those DC lines. So Texas is not part of FERC because all the interconnection from Texas to the rest of the U.S. is managed through DC lines. So they don't have FERC mandates because of the interstate commerce rules. The way the laws were written, they do not apply. So Texas does not fall under the mandate for FERC. So they are ERCOT and they've got their own rules, but they've decided to be separate. And then in the middle of the country, notice all the DC lines. Anybody know why those are DC? Those are very long lines, and it's really hard to maintain synchronism between the East and the West, so why bother? The West Coast is not in sync with the East Coast, but we can move power back and forth, and we do it through DC links. So that's how you break apart the actual requirement that they be the same.
So those are the 400 plus miles?
Yeah, those would be 300, 400, 500 plus miles. I mean, if we think Maine is a big state. Well, not once you start going past even Connecticut, right? Maine's a pretty small state. You go out to the middle of the country, there's some really big states where it's, takes, well, Texas, I think you go from one tip to the other, it's like 1,200 miles. So.
Those are the highest voltage class in the U.S.?
Nope, the highest voltage class tend to be here in Ohio. So in the Midwest, they've got a bunch of 765 kV AC lines there. The DC lines would be higher, but they're usually, if you go pole to pole, but if you go pole to ground, like Ayers Sandy Pond is a plus minus 450 kV. That doesn't sound like that much, but remember it's plus to minus. So if you went across two poles, it's 900,000 volts. But from phase to ground, right, it's different. So it's just a little bit of a different approach.
DC lines are fairly new, right?
Nope. DC lines have been around for, well, if you go way back, Edison had DC lines way back in, but those were all low voltage. High voltage stuff, they've probably been around for 40 or 50 years.
So what did they do before?
They didn't connect. They wouldn't interconnect. You couldn't connect the east and the west. Just didn't make sense. You couldn't do synchronism, so you just didn't even bother trying. And that is it for Chapter 6. So, you have a homework due. You have a test to talk about. When would you like your next test? I would propose, just for timing purposes, We can do a review on Tuesday and then have the exam on Wednesday, which would mean the homework is due on Tuesday. It's a non-trivial homework. It's probably going to take you several hours to complete it. The homework I gave you. Several hours. How long did it take you to do the lab? Okay. Did you have any G's in there? Okay. I wouldn't do that. So, what do you think? You want to test on Wednesday? The other option would be to have the test in class on Thursday and then do the review on Wednesday. But you only have an hour and 15 minutes, right? Or you can do the following Wednesday, but that's a big time gap between when the material is presented. So that's up to you all.
Can we move this homework to Thursday?
Yeah, is that an option?
This homework, yes, we can certainly move it to Thursday, but doing this homework is going to help you prepare for the test.
But I'm gonna do it Tuesday.
So let's just have it due to.
Okay, I don't quite understand.
Like Tuesday night? Yeah. I'm not gonna do it Tuesday at 6 a.m.
All right, so you want to have the homework due Wednesday before the test? Wednesday at 2?
Well, we can go over that could work.
See, that's the thing, which is if you don't have the homework due until Wednesday, you can't ask. I mean, you can always ask questions, but we won't go over.
But yeah, we won't go over it.
Homework Tuesday, review Wednesday, and review and Wednesday.
So have the homework due Tuesday, and then have the exam on Wednesday.
Yeah.
Well, let's vote. Okay, seems like it's overwhelming. So the test will be a week from yesterday. It's going to cover chapters 5 and 6, but you should be able to build Y-bus, should be able to do per unit, right? Should be able to do power triangles and three-phase power calculations. Have you noticed that that's been pretty darn consistent, right? All this stuff is building, and that's important. So don't forget about that. Any other questions? We have time. Does anybody want to talk about? Want to start chapter 7? Or? All right. Have a great day.